Hi there, this is Mr. Schnitzius, and in this video we are going to go over the North Carolina end of course geometry exam. In order to make it easier for you to review a particular question, I'm not going to go over all 60 questions in this video. Instead, I'm breaking this up into 4 different videos so that if you want to look at number 52, you can go to the 4th video and get there a little bit faster instead of scrolling all the way to the end of one much longer video. So we're going to do numbers 1 through 15 in this video. And number 1 says, what is the approximate area of a 70-degree sector of a circle with a radius of 8 inches? Well, you'll notice that I've drawn a picture for this problem. And we've got this 70-degree sector right here. I went ahead and shaded that in. And they told us that the radius, that's the distance from the center to the outside edge of the circle in any direction, either here or here, is 8 inches. So they want the area of this part. Kind of like if you were thinking, if this was the entire pizza and you cut out a slice with a central angle measure of 70 degrees, what would the area for this piece be? Well, in order to figure out the area of a piece of pizza, you first want to know what the area of the entire pizza is, right? And that's just a pi r squared calculation. This is the entire area of the entire circle. Similarly, the number of degrees in that pizza, if it's in the shape of a circle, is a full 360 degrees. We're not interested in the area of the entire circle. We're only interested in the area of the purple part. So that purple part is a part of the entire circle. So 360 degrees is the angle measure of the entire pizza. Pi r squared is the area of the entire pizza, but we want to know what the angle measure for just the part that we shaded in is at 70 degrees. And if we can fill in these 3 pieces, the central angle measure over 360 degrees, and we know what the full area of the circle is, then we'll be able to get what the area of that sector is. So this is the proportion that you can use. And we're going to set that proportion up over here like so. 70 degrees over 360 degrees equals, we're going to let x be our sector area, and then we're going to put the full area of the circle, pi times 8 inches squared. So part over whole for the degrees equals part over whole for the areas. Well, just like any proportion, we want to cross multiply this. So when we do that, we're going to have 360 times x equals 70 times pi times 8 inches squared. So we're going to work this part out in the calculator. 70 times pi, 70 times pi times 8 squared. All right, so as a decimal, that comes out to be 14,074.3. So we're going to put that down as part of our work. Let me make sure what I know what that value is, 14,074.3. And now in order to get x by itself, we want to divide both sides by 360. So if we work that out in the calculator, divide by 360, that comes out to be 39.0954. That is closest to 39 inches, so that is why number 1 is C. All right, I guess we can put 39 inches squared there also as an approximate. Okay. Number 2, segment JK and LM are perpendicular diameters of a circle. They are each 12 inches long. So you may have noticed something here. When they don't give you a picture, you want to draw a picture, okay? You want to draw out a picture. That way you'll have something to label. What is the approximate length of chord LK? Well, we're going to go ahead and draw in that chord LK. And I'm going to label that segment LK that we're looking for as X. All right, so what do we need to do with this given information if we're told that JK and LM are perpendicular diameters of a circle and they are each 12 inches long? Well, there was a theorem that you learned when you were learning about circles. If a diameter, sorry, that's a typo. If a diameter of a circle, there we go. If a diameter of a circle is perpendicular to a chord, then the diameter bisects the chord. Well, let's go back and review what a chord is. A chord is a segment that joins two points that are on the outside of the edge of a circle. Segment LK is a chord because point L is on the edge of the circle and because point K is on the edge of a circle. Well, if you look at what the diameter is, though, segment JK is made up of connecting 2 points, J and K, both of which lie on a circle. So every diameter is actually a chord also. So this theorem actually works for two diameters also. If diameters of the circle are perpendicular to each other, then they bisect each other. That means that I'm going to put point C here since this is in the center of the circle, okay? So that means that from L to C is the same as from M to C. Why? Because these two diameters make this right angle right here. So what does that tell us about segment LC? Well, if the diameter is 12 inches long, this segment right here would be 6 inches long, okay? That tells us that the radius of this circle is 6 inches. Well, segment CK is also a radius, so that also has to be 6 inches. Any two radii of the same circle are congruent to each other. So what do we have now? We have a right triangle. Well, how do we solve for the missing side in a right triangle? When we know two sides, we use our old friend a squared plus b squared equals c squared. That's the Pythagorean theorem. So we're going to have 6 squared plus 6 squared equals c squared. So 36 plus 36 equals c squared. That's 72 equals c squared. And if we do the square root of both sides, the square root of 72 comes out to about 8.5 inches. That's how we get the answer D. You also might notice that if this is a right triangle, we have a right angle right there. That's how we knew we could do the Pythagorean theorem. If this is a right triangle and these two sides are congruent, then the angles opposite them have to be congruent also. Well, we've already used a 90-degree angle for our 180 degrees that these three angles have to have their measures add up to. So that means we've got 90 degrees left over, and if we split that in half, we've got 45 degrees and 45 degrees. Hey, this is a 45, 45, 90 triangle. So in a 45, 45, 90 triangle, you know that this side and this side, the legs, are exactly the same. So since those are legs, I'm going to label those with L. If these are L and L, then this length right here, LK, is the length of the leg times the square root of 2. Well, if we know that the length of the leg is 6 inches, then we can substitute that right here, and that would be 6 times the square root of 2. And if you do 6 times the square root of 2 in your calculator, you also get approximately 8.5 inches. So this is a nice problem because there's actually two different ways of solving it out. All right, let's look at number 3. A rectangle contains two inscribed semicircles and a full circle as shown below. Sorry that on the PDF of this, which part was the shaded area didn't really show up. So that's everything that's either the circle or the two semicircles is supposed to be shaded. If a point is chosen at random inside the rectangle, what is the approximate probability that the point will also be inside the shaded region? Well, you learned about geometric probability recently. That was in activity 42, the very last activity that we learned about. And we learned that a geometric probability is going to equal the shaded area divided by the total area. Now, in order to figure this out, it's going to be important to be able to use these radii, okay? See, we saw in the last problem, no matter where you draw the radius, it's going to be the same. From here to here is 6 inches, just like from here to here is 6 inches, just like from here to here is 6 inches. So it's the same way in this problem. If the radius is 3 units, then the distance from here to here is also 3 units, and so is the distance from here to here. Then, since the radius of this semicircle is 3, we can write a length of 3 from this center to this outside edge, and then also from here to here. So that means that if this radius is 3, these two radii make a diameter that's a length of 6, and this radius is 3, then this whole side is a length of 12. Similarly, we could draw a radius here that was 3 units long. We could draw a radius here that was 3 units long. And so that would give us a length of 6 for the height of this rectangle. So it's actually easier to do the total area. This is a rectangle. So the area for a rectangle is the length of the base times the height of the rectangle. So that would be 72 units squared. Well, now we need to get the shaded area, okay? What shape is our shaded area in? Well, it already says up here, full circle and 2 inscribed semicircles. So we've got one circular area with a radius of 3. We've also got 2 inscribed semicircles, but if we take those 2 semicircles and put them together, it's going to be a full circle. So that's going to be 2 times the area of one of the circles with a radius of 3 units. So we've done the area for a circle before. That's pi times the radius squared. So let's see. 3 squared is 9, so this is going to be 9 pi. Sorry, that's not inches, that's units. 9 pi units squared. So that's going to be 18 pi units squared. And so let's see about what that comes out to. If we do 18 pi as a decimal, that's around 56.549. And so now we just need to drop this into this nice fraction. So 56.549 units squared over the total area, 72 units squared. And let's see what that comes out to be. We're going to divide that decimal we got by 72. It's about 0.785, which is how we get B 79%. All right, let's check out number 4. Number 4 says the midpoint of segment PQ is R. R has coordinates -3, 2, -1, and P has coordinates 4, -6, -6. What are the coordinates of Q? So I put this question on here anyway, even though you are not going to need to know about 3-dimensional coordinates on the final exam. So we're not going to work this problem out all the way, but this is a good opportunity to solve this question as if it was just two-dimensional coordinates. Okay, so we could sketch out a graph for this. So here's our XY coordinate grid. So R is at -3, and this is just going to be a sketch. This is by no means going to be perfect. R has coordinates -3, 2, and P has coordinates 4, -6. So there's R, and there's P. And we're looking for the coordinates of point Q. So we know that point Q is going to be somewhere up here in quadrant 2. So since this is going to be a multiple choice test, we can use some of our multiple choice tricks to help us. Anything that's not in quadrant 2, we can get rid of, such as C or D. And really, you can get that the answer is A just by thinking about the reasonability. If I put -3.5 and 4, that point is right there. There's no way R is halfway in between these 2 points. So we can get rid of that, and we can go ahead and check out that it's answer choice A. So what could help you on this question if you weren't doing it with a guess and check kind of scenario? Well, on the formula chart that you're going to have for the final exam, the midpoint formula is x1 plus x2 divided by 2, comma, y1 plus y2 divided by 2. So we know that the coordinates for R in the xy grid are -3, 2. We can label the coordinates for P as x1 and y1. So that would be 4 plus x2 divided by 2, comma, y1 is -6 plus y2 divided by 2. And see, now we have two different equations we can solve. To solve for what x2 is, we just need to take the x value from the midpoint and match it up with the x value from the midpoint formula. So -3 equals 4 plus x2 divided by 2. Well, we can multiply both sides times 2. Those cancel out. 2 times -3 is -6, so we've got -6 equals 4 plus x2. We want to know what x2 is, though, so we've got to move that -4 over. So now we've got the value for x2 is -10. So that's how we get x2. And we're going to do the same thing with the y value of the midpoint. So that's going to be 2 equals -6 plus y2 divided by 2. So multiply both sides times 2. That's a good first step. So now we've got 4 equals -6 plus y2. If we add 6 to both sides, then we end up with y2 equals 10. All right. So here's number 5. A cone has a radius of 12 centimeters and a height of 9 centimeters. What is the approximate lateral surface area of the cone? To calculate the lateral surface area A, use the formula area equals pi RL, where R is the radius and L is the slant height. So this formula is on your formula chart. We know that the radius and height of a cone are perpendicular to each other. We also know that we're going to need to solve for the slant height. The slant height in a cone is the distance from the very top of the cone, the vertex, down to any point on the base edge, on any point on the circle. Sorry, that's not an edge. Any point on the circle. Well, if you notice, we've got a nice right triangle right here. So they tell us that the radius is 12 centimeters. This picture is not going to be drawn to scale, and that's okay. We're just trying to be able to put a picture to the information that we're given here. So since this is a right triangle between the height, the radius, and the slant height, we can do the Pythagorean Theorem to solve for the slant height. So that's going to be 9 squared plus 12 squared equals the slant height squared. So that's 81 plus 144 equals the slant height squared. 81 plus 144 is 225. Then to figure out what the slant height is, we need to take the square root of both sides. So the slant height is going to be 15 centimeters. Okay, and now we're ready to use this surface area formula. That is pi times the radius, 12 centimeters, times the slant height, 15 centimeters. And let's throw that into the calculator and see what we come up with. Pi times 12 times 15. And 180 pi is about 565. So that's how we get D. All right, number 6 says a garden has the shape of an isosceles right triangle. The length of the hypotenuse is 24 feet. What is the area of the garden? Well, to find the area for the garden, we need the area formula for a triangle. So that's going to be area equals 1/2 base times height. The base and height of the triangle are going to be the sides that are perpendicular to each other. So that would be this vertical segment right here and this horizontal segment. So our job is going to be to figure out what these two sides are. Well, we've already seen that in an isosceles right triangle, that actually gives us a 45 degree 90 right triangle. So we can label our sides x, x, and x times the square root of 2. So we have to take this equation right here and solve it backwards. X times the square root of 2 equals 24 feet. To undo multiplying by the square root of 2, we need to divide both sides by the square root of 2. So let's get what that is as a reduced radical. So we want to multiply the top and bottom times the square root of 2. So that's 24 times the square root of 2. The square root of 2 times the square root of 2 is 2. So 24 divided by 2 gives us 12 times the square root of 2 feet. Our units here are feet. So we've got 12 times the square root of 2 for each of the legs. And now we can use those 12 times the square root of 2 for the base and height of the triangle in our area of a triangle formula. So let's work out what that comes out to. 1/2 times 12 times the square root of 2 times 12 times the square root of 2. And that gives us 144 square feet. So that's going to be B. Also, if you wanted to do this without doing the reduced radical form, if you just did 24 divided by the square root of 2, that's 16.9706. You could also get away with doing 1/2 times 16.9706. Since we were multiplying two of those sides together, we can square that, and that also gets us 144. All right, number 7. Number 7 says, in the diagram below, line J is perpendicular to line M, and line K is perpendicular to line M also. So let's go ahead. They actually already put those right angles in here for us. They want to know, what is the measure of angle 1? Well, we know that if this is a line, and the measure of a line is 180 degrees, then this right angle right here is adjacent to another right angle that's made up of the 51-degree angle and this mystery angle. I'm going to number this angle 2. Well, the measure of angle 2 plus 51 degrees is 90 degrees. Those are complementary angles. And if we subtract 51 degrees on both sides, then that tells us that the measure of angle 2 is 39 degrees. Well, we also know that we have a triangle that we've made here between angle 2, the right angle, and angle 1. So if the measure of angle 1 plus the measure of angle 2 plus the 90-degree angle have to be 180 degrees, this also reminds us that angle 1 and angle 2 have to be complementary. That's true for the acute angles in any right triangle. And so if we substitute 39 degrees for the measure of angle 2, then that could give us the measure of angle 1 plus 39 degrees equals 90 degrees. We can take away 39 degrees on both sides, and that would give us that the measure of angle 1 equals 51 degrees, which gives us the correct answer, C. There's actually another way to do this problem. If you remember back to the very beginning of this class when we were talking about parallel lines, okay, these two right angles are corresponding angles that are congruent. So we know that lines J and K are actually parallel to each other, and this angle, the 51-degree angle, and this angle 1 are alternate interior angles. So this is a good reminder that if two parallel lines are cut by a transversal, then the alternate interior angles that they form are congruent to each other. All right, let's look at number 8. Which pattern would fold to make a pyramid with a square base? Well, here is a picture of a square pyramid. What do we notice here? We've got one square base that I'm going to highlight in blue. So one square base, and we also have 4 lateral triangular faces. So that's the first thing we're looking for in our answers, is a net with 1 square and 4 triangles. So that's not A. because there's 3 squares. That's not B because there are no squares. That's not C because there's 4 squares. So without doing too much work here on this one, just identifying what shape the base is and identifying what shape the lateral faces are, we've got the answer. All right, so let's check out number 9 now. In the figure below, line WY bisects angle VWZ. The measure of angle VWY is 32 degrees. And the measure of angle VWX, the whole angle, is 117 degrees. What is the measure of angle ZWX? So this is the angle that we're looking for here. Well, when it says that ray WY bisects angle VWZ, what does it mean to bisect something? That means to split it into 2 congruent parts. So that means that this angle VWY, is congruent to this angle YWZ. Well, if those 2 angles are congruent, then angle YWZ must also measure 32 degrees. And so now, if we know that the total angle measure VWX is 117 degrees, well, we can add together the angle measures that we've used so far. 32 degrees plus 32 degrees is 64 degrees. Then we could take that 64 degrees away from what we have already, excuse me, we can take that 64 degrees from the total angle measure, angle VWX, and that would give us 53 degrees, which is why the answer to number 9 is B. All right, let's look at number 10 now. Number 10 says quadrilateral WXYZ is a parallelogram. The measure of angle W equals 40 degrees. What is the measure of angle Z? Well, this is a good opportunity to review some of the facts that we know about parallelograms and also review why we know them. We already talked about parallel lines cut by a transversal, and when that happens, the same side interior angles formed are supplementary. So an example of that would be angle W here, and also angle Z. Why are they same side interior angles? Well, if segment WZ is the transversal that's connecting these 2 parallel lines, they're both on the right of the transversal, and they're both inside the parallelogram. So these same side interior angles are supplementary, but since they're the consecutive angles of a parallelogram, that means that for any parallelogram, the consecutive angles are supplementary. What does it mean for angles to be supplementary? It's that the angle measures add to 180 degrees. So if the measure of angle W is 40 degrees, we know that 40 degrees plus the measure of angle Z is going to equal to 180 degrees. If we take 40 degrees away from both sides, then we've got the measure of angle Z equals 140 degrees. All right, let's look at number 11. In the diagram below, the length of segment PQ equals the length of segment MQ, and the measure of angle M equals 70 degrees. Well, we've seen this earlier with isosceles right triangles. In isosceles triangles, the angles across from the congruent sides are congruent. So if angle M measures 70 degrees, so does angle PQM. Okay, so we've already used 140 degrees of our 180 degrees that we have for triangle PQM. To figure out the measure of angle QPM, we can take 180 degrees minus 140 degrees, that tells us that this angle in the top measures 40 degrees. So they want to know what is the measure of angle TQP. So we actually could have gotten that without this 40-degree angle measurement, although that's helpful. That's the measure of this angle right here that we have in blue. Oh, I'm sorry. I mislabeled the information at the beginning. Let's start over. Segment PQ is congruent to segment MQ. There we go. So now these two sides are the sides that are congruent. So these two angles, angle M and angle QPM, are going to measure 70 degrees. So now we can use that same work that we had shown. It's just the 40-degree angle is going to go here for the measure of angle PQM instead of up here, okay? Now we're looking for the measure of angle TQP, which is going to be here. Well, what do we know about angles TQP and angle PQM? They have to be supplementary. They form a linear pair. So if we already know that we use 40 degrees for the measure of angle PQM, we need to do 180 degrees minus 40 degrees, and that will give us the answer 140 degrees. So that's how we get C. All right, let's look at number 12. Number 12 says, what is the measure of an interior angle of a regular polygon with 16 sides? So there's a couple of things that you want to know in order to solve this problem. The sum of the interior angle measures for a convex polygon, that's all the polygons that are covered in this class, the insides equals n minus 2 times 180 degrees. We also know that a regular polygon is a polygon that is both equilateral and equiangular. So that means that all 16 of these sides that are numbered are the same length, and therefore all 16 of the angle measures, if it's a regular polygon, are also congruent to each other. So we want to find the measure of just one of these interior angle measures if we have a 16-sided polygon where all the sides are the same measure. Well, we're going to take this value for the number of sides, and we're going to set that equal to n. So to find the sum of the interior angle measures, we're going to do 16 minus 2 times 180 degrees. That tells us that there would be 14 non-overlapping triangles that we could fit inside of this 16 gon. And how many degrees is that? It is 2,520 degrees. But notice that is not one of the answers because they don't want the sum of the interior angle measures. They want the measure of only one of these interior angles. How many congruent angles are there? Well, there are 16 angles to go along with these 16 congruent sides. So if we divide that by 16, then we get as a decimal, we get as a decimal 157.5 degrees, which is answer choice C. All right, number 13. M is the midpoint of segment RS. Segment R, the length of segment RM equals 3x plus 1, and the length of segment MS equals 4x minus 2. What is the length of segment RS? Well, what do we know about the midpoint of a line segment? It divides it into two congruent halves, so that's telling us that the length of segment RM is equal to the length of segment MS. So that's going to give us 3x plus 1 equals 4x minus 2. If we can figure out what x is, then that'll get us closer to our answer. So we're going to move our x's over to the right side. Going to move our -2 over to the left side. So we get some values that cancel out. We get 3 equals 1x. Okay, that's nice. So that's telling us that x is 3. So now we can get the length of segment RM. That's going to be 3 times plug in the 3 plus 1 is 10. And from here, the easiest way to solve this problem is say, well, if this is the midpoint, from R to M has to be the same as from M to S. That's actually true. And you can just double check that quickly. 4 times 3 is 12, minus 2 is 10. And now the length of segment RS, using the segment addition postulate, is the length of segment RM plus the length of segment MS. That's 10 plus 10 is how we get a total length of 20. All right, number 14 says the slope of a line tangent to a circle is 2 over 5. What is the slope of the line that passes through the point of tangency and the center of the circle? So there's some good vocabulary to review in this problem. Common theme in this video is draw out the picture. If they don't give you a picture, draw one out. So here's a picture of a circle with a tangent line. This line is a tangent line because it intersects the circle at exactly one point called the point of tangency. All right. So it says the tangent line is perpendicular to the radius of the circle at the point of tangency. So when it talks about the line that passes through the point of tangency and the center of the circle, that's just the radius. That's the radius of the circle, right? The radius goes from the center to the outside edge. So here's our radius, if this is the center. And there's a theme that we learned when we were learning about circles that says the tangent line is perpendicular to this radius, right here at the point of tangency. The point of tangency is simply the point where the tangent line and the circle intersect. So they're telling us that if the slope of this original line is 2 over 5, what is the slope of this radius? Well, what do we know about the slopes of perpendicular lines? If two lines or segments are perpendicular, then their slopes are opposite reciprocals of each other. Well, opposite means if this slope is positive, then this slope is negative. Reciprocal means we need to take this fraction and flip it around. So when we flip around 2 over 5, we get 5 over 2, and that gives us a slope of negative 5 over 2. That's how we get A. All right, let's check out number 15. Which statement is logically equivalent to the given statement? If a quadrilateral is a rhombus, then it is a parallelogram. Well, logically equivalent statements are statements with the same truth value. So let's think about what's true about, or if this original statement is true or false. If a quadrilateral is a rhombus, okay, here's a rhombus, then it is a parallelogram. Well, what are the facts about a rhombus? All 4 sides are congruent. Opposite sides are parallel. Right there, that's enough to know that it's a parallelogram. So this is a true statement, okay? So let's go through these and see if we can find a true statement. If a quadrilateral is a parallelogram, then it is a rhombus. Well, it's pretty easy to show why that is not true. Here is a parallelogram. This parallelogram does not have 4 congruent sides. The top and bottom are longer than the left and right, so that shows that this is not a true statement. B, if a quadrilateral is not a rhombus, then it is not a parallelogram. Well, this picture disproves answer choice B as well. This is not a rhombus, but it actually is a parallelogram, so B is false. C, if a quadrilateral is not a rhombus, then it is a parallelogram. So this picture might tempt you into thinking that C is true, but let's see. Let's just freehand. Or actually, let's make a trapezoid. Okay, is this quadrilateral a rhombus? No. So the hypothesis for part C is met. But is it a parallelogram? Also no. So that goes against part C. So hopefully D is right. If a quadrilateral is not a parallelogram, okay, so let's test that out on this quadrilateral down here. This is not a parallelogram. Is it also not a rhombus? Hey, that's actually true. This is actually the contrapositive form of the original conditional statement, where you switch around the hypothesis and the conclusion, but you negate both of them. You put not in to both the first statement and the statement after the comma. All right, that's it for numbers 1 through 15. Hope you enjoyed this. Good luck studying for your final exam.